All right, folks, welcome back. Let's get after this here. Differential equations practice test 2020. That means the actual test is near. One last time you get to hear me say this. All the cool kids call this Diff EQ, so feel free to use that as a nice abbreviation if you want. And then, of course, it's yours truly doing this work. I really like this practice test, folks. There are a couple questions on here that students tend to struggle with, and I hope that through my dynamic and engaging commentary, you will find these problems a little bit easier in the future. Okay, so we have a differential equation here. It's dy dx equals 1/2 of the quantity x times y. First thing I notice here is we've got no restrictions on x or y. We don't have anything in a denominator. We don't have anything under a square root symbol. So based on the differential equation alone, x and y can be any real number. All right, let's now move on to the first part of this question. On the axis provided, sketch a slope field for the differential equation at the indicated points. Before I do this, I like to make a table of values. I find that very helpful. So here goes. Now to find the values for the slope, all I'm going to do is multiply the x and y coordinates together and cut it in half. Okay, so those are my values for the slope at each of these different points. Let's go ahead and sketch these on the slope field. All of them that are 0 means we have a horizontal segment, so those are pretty straightforward. Now we have to make sure we're careful here. We've got some, like let's look here, the difference between -2 and -1, that slope. What's important here is that you show a difference between those two. Your slope doesn't have to be perfect. That's a slope of about -1, and that's a slope of about -2. It just has to show that this one is steeper than this one. Now here are the rest of the slope segments. Okay, there's our slope field. Let's move on to part B of this problem. It says solve the differential equation for y equals f of x using separation of variables. So you know that I've got a 4-step process that I like to use. So we're going to separate, we're going to integrate, and then we're going to rewrite. So let's see what that looks like here. Original differential equation, xy divided by 2, or 1/2 xy. Variables are now separated. Let's write our antiderivative symbol there. Time to integrate. Now let's rewrite this bad boy by exponentiating both sides. I've already tagged that as C sub 1, and the reason why is a little foreshadowing here. I kind of knew that this bad boy was going to happen, and we could just call that C. So now I'm ready to rewrite this whole thing. I have the absolute value of y equals some constant C times e to the 1/4 x squared. We can go a little further here, and I'm going to write this as just y equals C times e to the 1/4 x squared. And I have to justify that. I'm not just allowed to erase an absolute value symbol. So I'm going to justify that here. If y is greater than or equal to 0, then c will be greater than 0. If y is less than 0, then c will be less than 0. And that's basically taking care of the piecewise nature of the absolute value of y. Okay, now we've solved this. This is our general solution. And we're ready to move on to the next piece of the puzzle here, which is part C. Solve for a particular solution through 0, 1, and then sketch the solution on the graph. So in order to do that, we're going to sub the point 0, 1 into the general solution, which is y equals C times e to the 1/4 x squared. E raised to the 0 power is 1. So this works out very nicely. That just gives me a constant of integration of 1. I can now state the particular solution is y equals e to the 1/4 x squared. Now this isn't quite done. I've told you this before. Whenever you write a particular solution to a differential equation, you need to state the domain on which it's valid. We have no issues in this function with domain restrictions. We also identified no restrictions back with the original differential equation. So we're going to say that this is true for all x. And some people might say, that's not necessary with this function, but I would argue that it's a good habit to get into anytime you're writing a particular solution to a differential equation. All right, let's go ahead and graph this bad boy on the slope field. This was our initial condition, and we're going to kind of come off this way and just follow the pattern of those slope field lines. And there you have it. Let's now move on to part D, and this is one that I'll tell you, students tend to find this question tricky. Take a look at this. It says find this thing in terms of x and y. I hope you remember what this is, folks. Yeah, this is Leibniz notation for the second derivative. There was, and I specifically am reminding you of that, there was a question on the AP exam a few years ago where students missed it more often than the graders expected. And they think the reason for that was that it involved Leibniz notation for the second derivative. So I want to make sure that doesn't happen to you. Okay, so we need to find the second derivative here. I'm going to write this out very specifically in a very mathematical notation. You may not write it this way all the time, but I just want to make sure you understand where this is all coming from. So I'm showing you here that we're taking the derivative with respect to x of both the left-hand side and the right-hand side. This quantity right here was the original first derivative dy dx. So when we do that, we get the second derivative. Now be careful. I hope that you see this before I even mention it. This is a product. So we better be using the product rule here. We're going to have 1/2 x times dy dx plus 1/2 y times the derivative of x with respect to itself, which is just 1. So let's go ahead and simplify this here. Let's write this as, on the left-hand side, y double prime equals 1/2 x times y prime plus 1/2 y. Now, in this form, it is correct, but I want to share with you that it doesn't meet the requirements of the problem. The problem say write the second derivative in terms of x and y. So I need to substitute back in my expression for y prime, and that's from the original differential equation. So now I have y double prime equals 1/2 x times 1/2 xy plus 1/2 y. Let's go ahead and clean this up a little bit. Y double prime equals 1/4 x squared times y plus 1/2 y. And that will get you full credit for finding the second derivative in terms of x and y. Another tricky problem, part E. Let's take a look at what we're asked to do here. Determine the concavity of all solution curves for the differential equation in quadrant 2. Give a reason for your answer. Well, this is something we haven't been asked to do for a while, and we're at that point in the course where we can see questions from any different section of calculus coming at us. So when I see a question about concavity, I'm thinking that we have a test for concavity. And the test for concavity is we analyze the second derivative. We look to see if that second derivative is positive or negative. Fortunately, we have an expression for the second derivative. We just came up with it right here. So we're going to be able to use that. The next thing we need to consider is this. What's going on in quadrant 2? Well, in quadrant 2, x is less than 0, y is greater than 0. So that's going to factor into our decision. Let's go back and look now at y double prime. We have y double prime equals 1/4 x squared y plus 1/2 y. Now let's analyze each of the quantities in here separately. We've got this quantity, and this quantity. Well, x is less than 0, but we're squaring it, so that becomes a positive. Y is already positive. So these are all positive quantities. Because those are all positive quantities, when we multiply them or combine them, we will end up with the following. Y double prime will be greater than 0 in quadrant 2. So all solution curves will be concave up. Okay, so one thing that might be nice to go back and look at is we already sketched a particular solution. Does that match what we just said about concavity? And it sure does. We sketched this, and in that quadrant, in quadrant 2, it appeared to be concave up. So that's just a nice double check. Before I go on to page 2 here, I just want to mention one thing. The practice test here says you may use your calculator. Justify all answers, no justification, no credit. We always say those things, but the calculator one is particularly interesting. I'm going to be honest with you. I haven't decided yet whether or not this test is going to be calculator or non. In fact, in this practice test, there's only one question where I'll even use a calculator, and that's only to get an approximate answer. You should be able to do everything without a calculator other than approximate some of your answers with the work we do with exponential growth. Okay, that's it. We're going to shut this one down and then move on to page 2.